Hey everyone, welcome to the Flipped Friday lecture for March 20th. So that's March 20th. We have exam 4 coming up, and so at that time we'll be in the lab, and so I'm going to start the lecture here on time series and recurrent networks, and I'll deposit the little video link here on this portion of the course website once we have finished that up. So without further ado, let's jump into time series and recurrent neural networks. So everything that we've been working with up until now has dealt with information that doesn't have a time component. So if you're considering looking at an image, for example, right, you classify an image or you classify a data vector from the iris data set, you just pass in one vector which has all the information you need in that one sample to make a prediction. And the idea is this is all the information is available to you all at that instant. And as a result, these kinds of tasks, right, are common. You just have this issue that there's no temporal or time component. But once you start to introduce problems that have some element of temporal progress going through time, then in that case we now turn our approach to trying to figure out how would a neural network make sense of this kind of data. So some data naturally have some type of time component. So here I've got an example, right, of maybe a stock price over time, fluctuating, going up and down with market. And you can do classification or regression problems, but this is obviously a regression problem because we're trying to predict a particular target stock price. And so at some point in the future, right? The idea is that there's time in the sense that all the input itself is spread out over time, but then even the thing you're trying to predict itself is also something that's sort of forecast, maybe in the future, or you're trying to predict it. And so there are different ways that you might try to do this, but lots of tasks have this issue to them. Predicting stock prices, maybe you're doing some kind of video analysis, maybe you're looking at progressions of weather patterns, lots of things, right? Anything that involves time is when we're trying to make a prediction, usually into the future, right? Because predicted data in that case is hopefully used to make future predictions, and that helps us hopefully solve those kinds of problems. So audio, right, music and videos obviously fit into, there's a lot of audio on that stream, but videos coupled with that, you can have audio and video together. A lot of natural language processing though, third one here. So this is a little different. We're not talking necessarily audio or video. The idea is that you're trying to process text-based data, documents, or other things that are arranged with natural language. We don't often think about that as having time, but if you do think about it for a moment, you will realize that's definitely involved. Because if I am ever reading through a document, right, I don't read through the whole document at the same time. Instead, I start at the beginning and I start to progress through it. And the idea is I don't see the whole document at one point in time, right? There is something where I have to progress through it through time and spread out my experience with that document over time. And so natural language processing has a lot of that flavor to it. The same way that I can't listen to simultaneously all moments in a song at the same time. I can only experience it as a progression through time. Likewise, when I'm watching a movie, I can't watch all scenes in the movie simultaneously. I can only see them as progression through time. Lots of other things, weather, heart rhythms, brainwaves, bird flying, blah, blah, blah. There are lots of different things that have this kind of temporal data idea, right? There's an aspect of temporality to it. So we have to think about what might need to change or what might need to be different about our neural network architectures to be able to deal with this kind of data. Some data just cannot be analyzed using a single measurement alone, constrained in time to a finite, everything's in one moment type of prediction. Usually what this means is that information from the past, things we've seen in the past, are needed and therefore maybe need to be remembered, recalled. They also then need to be stored in some way for that recall later on so that they can be used to make a good classification call or to solve a particular regression problem. We want to ask the question, is this a video about a cat? You can watch the entire video. You're probably going to remember some key scenes, learn to store some information when cats appear. It gets to the end of the video and somebody asks you this random question, was there a cat in the video? You pull out what you've remembered now to be able to make this future prediction, right? This prediction in the future about what that thing was from the past. So past information often leads into these future predictions. So the question is whether we need to store information or not, how we need to do that. A lot of that will be task specific, but it's an important question to ask. Like, how do you remember or pull this stuff from the past? How do you store things in this past information effectively? And what should we store and what should we not? Because some of it may be relevant and some of it may be not relevant in the input stream that we're receiving. So these are just sort of questions that might come across when we're trying to investigate this. How do we do this practically though? So if we're talking about neural networks, one thing that we know is that the time series data, they would then consist of feature vectors just like we've been observing, but they have to be discrete time points. And basically the system is broken up in these discrete time points. The simplest analogy is drawing between image processing that we're doing now and then going to video. Naturally, rather than dealing with one image, you have multiple images all stacked through time. And so each time point has this discrete image associated with it. But naturally, there are relationships between the images across time as well, and we're hoping we can use that information in some useful way. We can just adapt our current architectures that we have been exploring so far, all of which have been feed-forward architectures. So this could be convolution architectures, right? We could make sure that not only do we feed the model through for, if it's a video, a frame of videos, we may say there's, 3 frames in the past, 2 frames in the past, 1 frame in the past, and then the current frame in the video. It's kind of like saying that we have this short buffer, you might say, of video frames that we can store, and this can allow us to now process that whole piece or that whole chunk of temporal information spread out across time as one representation that represents this whole stacked set of points. So notice this blue arrows here don't really indicate any kind of interesting connections like connection weights, right? There's no direct connection between those units. That's why they're just colored in blue here. They're just saying, right, that this frame, right, you have a delay of 1 time step from the frame that was right before it. This one has a delay of 1 time step from the frame that was right before it. But the idea is you could just read this information in as just one big contiguous chunk of information. We basically treat this as such. And the idea would be there's some kind of output prediction that needs to be made on that particular time step. Like when we get to this frame, we're trying to ask a question of some kind or classify something from this information. And if the video happens to be, wider than these, 4 frames that we're plugging in here, we can build what's called an autoregressive model, which means we might just take this neural network and just kind of slide it along through the frames, and we would produce an output basically for every group of 4 frames that we find in the video. So the first 4 frames would kind of go in and you produce a prediction kind of associated with that 4th frame in some ways. You can't start until you at least have the buffer maybe kind of full, or you could start with the first frame here and then zero out all of the earlier frames and maybe have an output from the very beginning. There's different ways that we can do that, right? But if we fill in with a bunch of zeros, put the first frame here, I guess we put it here at first, right? Put the first frame in, get an output. Now we get to where we have 2 frames, so we put the current frame and the past frame here, flow through, get a prediction. We go 3 frames, get a prediction, 4 frames, get a prediction. And when we get to the 5th frame, the idea would be we'd put frame 5 in here. We would keep the frame 4, frame 3, and frame 2, but frame 1 would just be removed or truncated, right? We would lose that. But the good thing about this approach is that you could do this for an arbitrarily sized video, right? You're only looking at 4 frames at a time, but you're taking your little neural net and making sure that you apply that 4-frame neural network across all possible windows of 4 frames and using that to try to make some kind of prediction. Basically, we're just unrolling the time component in space to some degree, right? And then sliding it along to make this thing called an autoregressive model. So we're gonna, the idea here, notice, is that this is discontinuous or discrete in some ways. We treat each time point as a discrete piece of information that we're reading in, a discrete feature vector. There are continuous extensions to this, ways to make it more continuous, but we're going to stick with the discretized state because most things in the end can be discretized at some level. For video frames, we don't have like a real continuous stream. We're only collecting so many frames per second or something like that. So typically, these are discrete samples when it comes to most real-world data anyway. Now, there is one thing important we've got to think about here, though. What we're doing implicitly when we use this kind of architecture, we are making an assumption. We are making an assumption. It's called the Markov assumption. The idea is we've taken this network and we have to build an architecture. We have to fix the width of this architecture. How many frames or how many time points are we going to use all at once to be able to do the prediction? Because the larger we make that, the more time points we include, the more weights we're adding into the network there. And you're basically having to use more and more resources. And not necessarily all of that would be important, but sometimes it could be. And you're making an assumption, the Markov assumption. The Markov assumption means that you assume that for whatever window size you've chosen, as you're sliding along through this time series, that would contain enough time points that it would be adequate to make the kind of prediction that you want to make. You're making the assumption when you fix the architecture that architecture is sufficient, captures enough time points effectively to predict the kind of property you want to predict. And it turns out that if you make a wrong assumption about this size, you may not be able to predict the thing that you're trying to predict adequately. So it's just good to reflect on this for a moment, because if I was to do this for sort of stock prediction, you might say, and I make my window, this is my window of inputs. I'm allowing my model to see these. And remember, there's more weights associated, a bigger model if I need to capture more data. But if I use this model, I would be feeding in this area here in blue just to predict maybe that next time point, right? Get the output for the stock price on the next day, maybe, for each of these. Okay, well, if I build such a thing, I would be making the Markov assumption. I would assume that at least in this width of window, I have enough information to adequately make the prediction about the next day. Now, on some level, this probably does kind of make sense. I mean, you could see how in this particular case, you're looking at these up and down oscillations within the window. So it's likely that if I'm sitting here and looking at this, and then I get here right at this point, and I see that quick down inflection right before in that blue area, I go, oh, we must have just hit a turnaround point. It might be possible for the model to predict that the stock's going to continue to go down on that next step. It's volatile, there's some noise in there, so it doesn't always get this right perfectly, but the idea is it might do an adequate job. But there are certain trends and information there that it will eventually start to get wrong if it continues in this vein. If the window only stays this size, it's going to have a very hard time understanding more large-scale fluctuations. So you'll notice, for example, there is this general tendency for the model to for this time series to fluctuate up and down. It's almost like there's a sinusoidal pattern that's different from the very short frequency sinusoidal pattern in the noise. Right? There's this quick oscillation, but there's also this slower, back and forth type of oscillation. And if the window is short like this, you don't really get enough information to adequately start to predict what these longer term fluctuations are. So we might likely fail, right? The Markov assumption was correct about these short-term fluctuations, but it's not good for the longer-term fluctuations. In order to capture them, we really need a large enough window that could at least see that cycle of behavior happening so that we could predict the next thing down the road effectively. So it's important to keep this in mind when you make these kinds of models, because every time you fix your window size, you're making the Markov assumption, and you need to think about your domain task. If there's anything you know about it that you can use to make that judgment call about how long the window needs to be, you would use that to help inform your decision making. But you are always making this assumption because I can't make a model that's infinite in size, or here it carries an infinite number of inputs in a feed-forward architecture. I just don't have an infinite number of slots. So it's going to come to a point where I have so much data that I can't fit the model on my device anymore, and I'm going to have to do this autoregressive function where I slide it along the input, and I have to be able to make the Markov assumption. So this is something that just is inherently true about feed-forward architectures when they're applied to temporal data. You are making the Markov assumption. And this idea will come back a little bit later in some other architectures we'll look at in the next coming weeks. But for now, I just want to bring it up because if you just adapt the feed-forward approach that we've been using so far to time series data, this is the natural way you might try. And it does in fact work pretty well for many problems, as long as you do find yourself making a correct Markov assumption, that you make the right window size for your data set, right? If you do, you can end up in a good situation. In order to predict longer stretches of time, you have to, just slide that window along, right? And the idea to try to help deal with that in some way is you could also say there's sort of like a copy back connection, right? So if I needed to predict more than one time step in the future, right, not just the very next time step, and then maybe I would get the stock price for the next day, the real stock price, and plug that in again as the next input. Sometimes you need to make predictions further than just one day ahead. You could use sort of a copy back based approach, right? I could predict the stock price on the next day using the network, and then go ahead and trust that prediction, copy it back in as if it is the real stock price on the next day, and then continue in this cycle for however number of days that I'd like. This type of autoregressive property allows you then to predict for more than just one time step in the future. And this is usually how we would do this with a feed-forward network. You would just make a prediction on the short term, just the next frame, and you just feed that back in. And this is the case, this works well for things like stock prices where the inputs themselves are a stock price, therefore the output, the thing you're trying to predict, is also a stock price. Very many types of problems have this kind of nature to them where you're trying to predict the very same thing that you're actually putting in as input. Not always, but often can be the case. So if you do have this approach, you can have an autoregressive network that just slides across the input stream and produces predictions, and then could produce predictions for potentially an infinite number of future states. But you are still limited by that Markov assumption, right? And no matter what, the feed-forward architecture limits you to that. So the problems here, right? What are the problems? All inputs, first of all, in that process may or may not be useful. So for the stock price problem, maybe most all of them are useful, but not necessarily, especially if you're just trying to get the general trends over time. The short-term fluctuations may not be as important, right? Maybe if you were trying to figure out if it's a cat video or not, right? You only need to remember kind of situations where cats appeared or that a cat didn't appear. You don't need to retain all frames or store everything. Most of the movie may not have cats in it, right? So someone asks you at the end, was there a cat in the movie? Right? If there wasn't one, you don't really have any cat features you remember. If there was one, it's just on certain events. Of course, the whole video also could have had cats in it the whole time. So the question is like what's important and what is not. You have to pick particular moments in time. Those are when they're interesting. Maybe the first appearance of a cat, for example. You don't need to store the rest because now you know it's a cat video. But all these sorts of things are ways we have to think about how we'll allocate resources. Like inside the network, what kind of function would it be writing to try to solve the task? So did we pick the right thing, right? Did we pick that? Is that the thing we've gotten that we needed? So not all inputs are the same value. Some may not be very useful. Did we actually pick the right time to gather that information? And then we've got some other issues like relative versus absolute time positions. So if you're thinking about this feed-forward approach and sliding this window, one thing you got to think about is that like this similar pattern here of seeing a 1-1, like a 0-1-1-0, like that pattern also shows up here, 0-1-1-0 for these inputs. They're, those patterns, according to a feed-forward network, don't look the same because those are very different weights that are attached to those inputs. But actually, it's the same pattern now, just shifted in time. And so that gives you the idea that maybe I need to use this sort of relative understanding. Right? If I see that pattern appear, it could appear anywhere in the time stream. Maybe I need to use some sort of tool to correct for that. In some ways, really, convolution will help take care of this for you if you needed to. Because right now, we've been used to thinking about images where they look at a 2 by, like a region inside the image, and they slide this convolutional filter across the image. Here you could do a 1D convolution where you look at a little window in the input and you'd slide across all possible windows. And that can help you somewhat with this absolute versus relative time positioning. But even if that's the case, we sort of build a pattern matcher that can find these little subpatterns, we still are stuck with the other two problems of should we store it or not, and then do we store it at the right time. So these are things that a feed-forward network will struggle with just based on the architectural choices. It's always receiving all of the inputs, right? Every time. All the inputs here are active, therefore it's getting all that information. The weights are always contributing. They're all putting an input to the hidden layer. Therefore, if there's a lot of distracting information in there, it's going to see all of that distracting information. Likewise, did we pick that right time point? Well, basically all of those different time points that could have happened here for some videos, maybe it happens here for other videos. Each of those weight sections have to kind of adapt to learn that independently with a standard feed forward. You could use some convolution to help with this a little bit to make sure that those features become absolute, relatively positioned instead of absolute. But in the end, you're still stuck with the choice of when you should actually remember it, right? When I saw it the first time, or when I see it at the end. And that's something that needs to be solved. So all of these factors are going into that function and are problems with the feed-forward approach and can cause it to perform poorly in certain scenarios in a way, especially for very long time scale tasks, right? Things that take a very long time to deal with. So we need to probably move beyond the feed-forward architecture. And this is actually a very old concept. Recurrent nets have been around for a long time. So this is going back into 86, a method called the Jordan network. So this is the same year as the error backpropagation algorithm was published inside the Rumelhart-McClellan book. And so as a result, this has been around for a bit. They started to come up with what they called a simple recurrent network, but they started calling them Jordan networks after the author instead, because they're the particular architecture, and reserved the term simple recurrent nets for some other architectures. But Jordan wanted to call them these sort of simple recurrent networks at first, but then retain the name Jordan networks over time. But the idea here was that there would be another set of inputs that you would apply to your network. So you have the current time step, just the current time step or the current frame in your video maybe would be put in as input. You go through a hidden layer and you produce an output. And the idea is there's this additional input layer. First it would be 0, right? All zeroed out for the first time step when you look at the first frame. But after you process the first frame, whatever the output is, whether it's a classification or regression or whatever the output might be for that time step, you would then copy that information back and it would become a new input vector for the next time step. And this is highly reminiscent of what we call a sequential circuit inside of circuit design. You basically have a flip-flop which has access to its own output while it's calculating the next input in the circuit, which can cause it to toggle between different states. So the idea being is we just copy back the output. Maybe that's enough information to be able to trigger this kind of updating through time, very similar to a sequential circuit. And in some ways, this was an effective way to do it. It basically could, in many cases, use that output and know, okay, well, I just did this, so maybe I should process this input differently based on my past information. That being said, Jordan networks had some clear limitations to them. The most noticeable is that what you have is this input now going through that wide hidden layer. Remember, wide networks were very popular back then. So you've got that wide hidden layer. You're then compressing that information down to an output, and then you're storing the output. And that, for some people, raised some red flags. Like, why would we compress this down and remove information and then try to plug it back in? Because now whatever was here, we have to kind of maybe distribute it back out or unpack it back into some useful representation for the next stage. And that's a complex transformation maybe that needs to be learned. So instead, after Jordan networks, there came Elman networks. And Elman networks, this is what came to be known for a while as the simple recurrent network. Again, it's not actually what we refer to as a simple recurrent network today. We would just call them Elman networks. But for a while, this was the standard form. They came out in 1990. Basically, they were like Jordan networks. You would copy back something but instead of copying back the output into an input layer, you would copy back the activations of the hidden layer, and that would create your new context or input vector. And this would allow you to basically go through your problem in an autoregressive manner, and you could apply your traditional learning rules, right? Just using regular backprop. These are just copy connections, right? They just take the vector of activations from the previous time step, copy it back down, and use it as inputs for the next time step. And the same thing was true for Jordan networks, right? They were just using the output instead. But because you were using this more distributed and high-dimensional hidden layer representation, Elman networks were usually a bit more successful. But the big advantage of both of them, the main reason why they were successful for a while, is because they were compatible with error backpropagation. You didn't have to modify your learning rules in any way. The only thing that needed to be done was when you put those vectors in, you propagated them through, you calculated your loss, you backpropagated your deltas, and you could always multiply your activations on your sending side times your deltas on your receiving side to update those weights. Activations on the sending side times deltas on the receiving side to update those weights. Activations on the sending side times the deltas on the receiving side to update these weights. Right? All of that could be updated using the traditional error backpropagation algorithm. So because of that, they were compatible already with the existing learning methods that we were using in neural nets. So there was often some initial success with that. Okay, I'm going to go skip over this for time, but they did show that they could learn some interesting temporal relationships in natural language processing, going through sentences. It could learn how to separate, say, like nouns from verbs, and even different kinds of nouns could be separated into humans and animals, or maybe different kinds of non-alive entities, so things that are alive versus things that weren't alive. And that was literally what this tree is showing you, are just differences in like distances between the vectors in that latent space, right? So that's the vectors here at the hidden representation that gets learned by an Elman network that processes sentences. It learns to self-organize, and when in the presence of verbs, creates representations that are in this area of the space, live things in one area of the space, and then inanimate objects over another area of the space. So that's kind of interesting, right? It's able to cluster and learn these sort of semantic representations. Gives precedence to the idea that maybe there's really something to this. But we really needed to move to a general technique that could solve this in general. So moving beyond Elman, how do we make an architecture that could do this in general? And this is where the simple recurrent architecture really emerged. So rather than having any kind of copyback method, instead, to make a general architecture that can solve any of these kinds of temporal functions arbitrarily, we come with a simple recurrent network. The idea would be to take an input layer, right, like we have here, and so let me move this out of the way. The input layer basically takes its input, propagates forward. Now on the first time step, these would all be zeros, and so you just use this set of connection weights, and there's actually in this network a set of connection weights leading from these units back to these units. So that's like a feedback loop that comes in for these units. And then they would then calculate their activations and then send that forward to the output layer. On the first pass, it really behaves like a standard feed-forward net, because all these would be zeroed out to begin with, so you'd multiply 0 times all these weights, and they wouldn't contribute anything unique to the weighted sums. But on the second time step, the very next frame of the video or whatever is in the time stream, you would have those activation vector would get multiplied times this separate set of weights, and then added in with the weighted sum from the inputs to the hidden layer. So those weighted sums, they all get added together, and you add the bias weight in, and now you have a representation that's both some combination of the new input and being linearly combined with the non-linearly transformed data from the previous operation, from the previous time step. So this folds that information together over time. So rather than laying things out in a feed-forward way, you now have a method where you can feed things in one time step at a time, and that information is essentially being folded up on each time step into this hidden layer representation to try to deal with some kind of memory, build some kind of memory about what has happened in the past. And those activation vectors will change depending on the sequence of inputs. So the series of inputs you experience will change how those activation vectors evolve and also change the learning process. So this is a general architecture, and similar to proofs that we showed before, how if you had just enough hidden units on your feed-forward architecture, it could solve any problem to an arbitrary degree of precision that can be solved without using time. It does happen that the similar proofs hold for the simple recurrent architecture. There is some set of weights that can solve your problem, whatever it may be, that involves memory to an arbitrary degree of precision. You just have to have enough units in the hidden layer, and you have to find those weights. But there are some issues, and we'll look at some of that in just a moment. So you can kind of think of these as like graded state machines. Remember, if you think about sequential circuits, they're kind of like a state machine, right? They have a small amount of memory, right? A flip-flop can hold on to one bit. If you take a bunch of flip-flops together, they can hold on to a series of bits, and you can change those values over time based on new inputs. The idea is that hidden layer representation is kind of holding on to some information about where we've been so far, or what the state of the environment is, or the state of everything we've seen so far, and can evolve through a certain sequence of inputs. So like if we think about maybe making a cup of coffee, depending on our inputs, maybe we fill a cup, then we add cream, then we add sugar, then we stir, then we drink. Right? These are kind of things that we might do if we wanted to make a cup of coffee. But we could also fill the cup and then add sugar and then add cream and then stir and then drink the coffee. And the idea is that the hidden layer representations might diverge and change depending on those particular order in which we're observing things, but the network should be able to learn how to deal with creating these kinds of state representations that hold on to what has been accomplished so far in time. And unlike a standard state machine, which is discrete, this would be a graded state machine. Graded in the sense that we're saying it's continuous, right? It's dealing with floating point values, not with just bits, zeros and ones. So it's kind of a smooth type of state, right? States are a little more, they're smooth and continuous states, not discrete states. Now, maybe a little bit hard for us to kind of conceptualize, but the idea is we're using the finite state machine to kind of say it's an analogy, right? It's analogous to a discrete finite state machine, but it's actually a continuous graded state machine that we're creating when we make this kind of neural network. But the question remains now, how do we actually have learning rules for this? Because this is a very different kind of architecture from a standard feed-forward net. How do we handle the deltas for the hidden units, and how do we adjust those correctly? Because it's not clear, right? You've passed now multiple time steps of information through the network. What are the deltas? And we have lots of activations for that hidden layer, and they've changed over time. Which ones do you use? So it's not really clear exactly what needs to be done. But even back then, this was solved. So even in Rumelhart and McClellan's book, they had already thought about this idea and came up with the main tool for dealing with learning of this type of network. And they call it backpropagation through time. So it's the same learning rule we've been using all along, but we do have this additional component of time added to the structure. So to give a little example about how this might work, think about having two neural units. They're connected by these connection weights. So what we see is that neuron A1 is taking a weighted sum of the activation of A2 plus its bias weight, so you can, plus a self weight. So it takes its own activation, multiplies it times a connection weight value, some W here, adds it into A2 times some W here for the green one, also maybe adds in a bias weight, right? But that means that its net input gets calculated based off these two values, and then it provides its activation function. Likewise, A2 would take A1's activation, multiply it times this W for the blue, multiply its own activation times a W for the pink, add those together, add the bias, that would be its net input. Now we use its activation function. So this type of architecture has these recurrent feedback loops. Basically, all units in a recurrent layer have this property, right? That they're reciprocally connected both to themselves and to every other unit in that layer. But we are kind of sweeping under the rug the input and the output, right? Like just leave those alone for now. We're just imagining there's just a hidden layer here, and these activations are evolving through time. So on the first time step, we kind of have these, maybe they are initialized with some values or something from that first input, right? They'll get some input. That'll change and contribute something and create an activation value. And then they're not receiving any input from themselves because they would be initialized at zeros. But after that, whatever their activation values are for the next time step, it becomes the weighted sum of these reciprocal, right, these recurrent connections that come back on themselves in that layer. So you can see all four of those connection weights represented here. But that means if you have the activation vectors at time t minus 3 at the very beginning, then you propagate them one step in time. Now they become the activations at time t minus 2. You do it another step for the next time step, and so on for the next time step. If you look at that carefully, you can start to see that essentially that architecture is then a feed-forward type thing that's unrolled in time, right? That you're basically recomputing new activation values for those units, and they would be spread out in time. So the idea with backpropagation through time is to unroll that time component and store that in space. So we would actually calculate these activations, do the weighted sums, calculate the activations for the next time step, do the weighted sums calculations, the activations for the next time step, and you're storing all these activations for each time step because it creates a sort of feed-forward model. And if you have a feed-forward model, when you calculate any deltas, those deltas can be backpropagated backwards across those weights, and then those deltas can be backpropagated across those weights, which can then be backpropagated across those weights, and you end up having deltas as far back in time as you would like. And then you can always take an activation on the sending side times a delta on the receiving side and update that weight, -1 times that combination there, right? Because you want to go downhill in error. But the idea is you can use standard error backpropagation by unrolling your network from time into space. And this allows you, we call that then backpropagation through time, but it's really just error backpropagation. But there are some funny things that are happening here, okay? And we'll get to that in just a moment. So what this means is you basically have different kinds of tasks that could be represented and possibly solved using this kind of architecture. So some quick ideas here on how we would do that. So if you're thinking about different kinds of tasks, okay, some tasks like stock prediction have this natural flavor to them where you have an input, right, for each time step. You're kind of tracking the stock maybe for the current day, and you're trying to predict what it's going to be on the next day. So you'd have, the current day coming in. You'd have a hidden layer computation, and then to try to figure out what that needs to be in a higher dimensional representation space, and then you predict the output, right, what that's going to be on that time step. And then you shift to the next day where you'd receive the next day's input. It would then fold up or receive, right, if you're unrolling this in space, right, we take the time and lay it out in space, it would be receiving that information from the hidden layer's previous time step through that weighted connection, right? That's unrolling it from time to space. But that then creates the output on the next time step. And then we feed in the next day and get the output to predict the day after that. And we feed in the next step and puts the day after that. Such a task where you have this input-output mapping in this way, we call that many-to-many, because you have many days of input, and on every single day you're producing an output, so there are many days of output. So that's a many-to-many mapping problem, right? There are many inputs mapped to many outputs. But there are other kinds of tasks out there that you can imagine that could use this type of architecture, but sometimes you would use those layers in different ways. So one example is something we would call the many-to-one type of mapping. So many-to-one would mean you'd have many inputs. So all these input layers would be provided. But then we would explicitly make sure that we do not provide any of these output targets. There would just be the one final output at the end. So this is a many-to-one mapping problem. So to give an example of this, you could say, all right, I want you to read through this whole document, and I just want you to predict, is this a scientific paper or is it an English paper? Right? And so the output there is just one single prediction about whether this is a scientific manuscript or not, right? You have or I guess maybe you do the softmax, you have different categories you want to have it classified into. You're going to go through the text, like over time, folding up information in the hidden layer to try to keep track of things, because you can't see the whole document at once, right? You're sliding through the entire thing. But at the end of the day, right, you would actually and you have this architecture, right? So you're able to do this as long as the document needs to be. But at the very end, you would just make a classification about what that thing was, right? But you need this kind of representation built up over time to solve this sort of many-to-one type of task. So unlike stock prediction, like document classification could fall into this. You could also think of movie classification or song classification. There's you have to listen to a large swath of the data, see a large swath of the data, experience a large swath of the data, and then you make a prediction based on that at the end. And that would be like a many-to-one type of mapping. Now, other types of mappings, though, can also be made, right? So you could instead create something like for certain tasks, you would have a one-to-many mapping, right? So this is maybe not as intuitive, but you might just have one input, and then you let the hidden layer evolve over time, each time producing an output for each of these different ones. And you still have something where you can backpropagate deltas through this entire net and even update that initial input to hidden layer set of weights. What would be an example of this type of task? Well, sometimes it's something where maybe we're receiving an image as our input, and what we'd like to do is have the network generate a sentence, some natural language description as the output, because that would be some series of things across time. The idea is you provide the image, and then the network produces a word, right? So this is the image passed in. It says, this is a cat, right? It would just have these four words that would get generated over time. And so that would be taking a single input and mapping it to many outputs, and that would be an example of a one-to-many task. So this type of simple recurrent architecture, simple recurrent network, can be used to solve all three of these kinds of problems, right? Many-to-many, one-to-many, and many-to-one. And this same architecture, it just depends on how you use it then at that point, right? You can either provide those additional inputs or just set them to 0, you might say, for those remaining ones. And same thing for the outputs. You're not calculating loss or worried about the output. You only worry about it right at the end. Those weights are all sitting there and are only used at the appropriate moment. But those types of tasks, you can represent all three of them with this type of architecture. All right, but even if you do this, right, you know these different kinds of things, there are some problems that happen. First of all, you have all of the typical problems that would show up for feed-forward networks. They still apply for recurrent networks. So gradient optimization. You have to use fancy optimizers like Atom or stochastic gradient descent adapted with momentum and other sorts of things. Maybe you have to do some type of learning rate annealing. The issues of just trying to minimize on the error surface are still going to apply. Those don't go away. So those are still there. You also, in most complex tasks, are still working with nonlinear decision boundaries and functions. You can't get away from the hidden layer, right? Of course, in a simple recurrent net, it's hard to imagine it without a hidden layer. But you have to have that nonlinearity to solve complex tasks. So that's still a hard thing to do. Therefore, it's hard, right? So finding that set of weights can be tedious. You also can still end up with typical issues we talked about so far, overfitting or just issues generalizing well. You may need regularization tricks, right? Or data augmentation techniques to be able to deal with these sorts of things. So those are all still present, just like everything we've had with feed-forward. But recurrent nets introduce some additional problems on top of this, okay? They introduce additional problems on top of this thing. So what do they bring to the table that's new? There are two big issues that arise with simple recurrent neural networks. So one of the big issues is actually something called exploding gradients. So here's what happens, right? Weights are often reused during that error backpropagation algorithm, right? So this activation is flowing across this red weight multiple times, right? It's flowing across the blue weight multiple times. When something flows across a weight multiple times, you've got to keep in mind that whatever that activation is, if that weight was above 1, right, say is a value of 2, then you're taking an activation and multiplying it times 2. And whatever you calculate here, you multiply it times 2. And whatever you calculate here, you multiply it times 2. There is a strong chance that you can oversaturate and cause those to explode. They grow potentially exponentially as they flow through the network. So this actually causes problems. We've talked about how large magnitude values can cause problems in the past. They drive the weights very hard, make large weight updates, and unfortunately, large magnitude weights are kind of like an overfitting problem, right? They cause you to poorly generalize. You don't do as good of a job. And this is more likely to happen in recurrent nets because you have this repeated use of the weights over and over again. Normally in a feed-forward net, these would be different weights sandwiched between the layers, and so they could differentiate and have different magnitudes. But here, you're going to reuse that value. So if it's above 1, they have a tendency to push the activations higher and cause the weights to get driven even further to extreme values. Okay, so that's bad, not necessarily a great thing, and it's not. It can often lead to more learning instabilities. We also, though, have a problem when it is shrinking gradients. So it's not vanishing gradients. You still have vanishing gradients, right? Vanishing gradients were already there because we know this is kind of feed-forward like now. So yeah, vanishing gradients still a problem. On top of that, you have shrinking gradients. As long as the weights are below 1, right? So before it was above 1, could cause them to explode. If they're below 1, that means they're a fraction. Imagine this is, maybe 1/2. If it's 1/2, you multiply the action times 1/2, multiply the activation times 1/2, multiply the activation times 1/2. The activation values are fading and going down to 0, right? So that means that in that case, right, just as similarly how the deltas can go to 0, you can also have now the activations going to 0. And when that happens, you also stifle learning because you have to multiply the activation on the sending side times the delta on the receiving side. So even if the deltas are present due to whatever trick you want, right, that can still cause problems. So it's a non-trivial thing here, right? You're almost on the border where only weights of 1 are going to evenly balance these things. It's a little bit difficult to imagine this not being a problem when you're trying to minimize error. It's very, very difficult. And you're trying to ask the network to learn a very complex function. It needs to know what information to store, what information to rearrange, what needs to be protected. How does it do all of that, even in the presence of these different things? Because of that, simple recurrent neural networks are actually sometimes very difficult to train. The idea is that we have in this raw form an architecture that can, in principle, solve any kind of time series problem, right? There is a set of weights that exists. But unlike even the feed-forward version, where it was already hard enough, we now have these additional problems of exploding and shrinking gradients on the table. And that does cause even more learning instabilities than we get with typical feed-forward approaches. So when that happens, we're going to have to heavily lean on inductive bias to help us fix this, because we need some technique that's going to make the network likely to learn the types of functions that we want it to learn. The question then becomes, what kind of functions do you want it to learn for time series data, and what kind of modifications can we make to the architecture to allow it to do that? It's very similar to asking the question about images. What is the kind of architectural change I need to do better on image data? At least translationally, positionally, invariant representations. What about these? What kinds of representations do we need? All right, so for that, there is an architecture that was developed. It's called long short-term memory. And I'm sort of giving you this all at once here, right? So the idea is that LSTM, or long short-term memory, is a drop-in replacement for simple recurrent networks that includes an inductive bias of the kind that works well for temporal data, right? It's useful. Just like convolution was useful for image data, LSTM is the most successful architecture for time series data, even to date. And notice the dates I'm putting on here, 97 and 2000. So these were not developed until right around the turn of the century, but they still have now persisted. 26 years later, they are still really the cutting edge in terms of recurrent neural network architectures. There are some other competitors out there that can do it a little more efficiently for about the same, for fewer parameters and still get the same performance, but oftentimes they haven't shown better performance, right? They just basically do about the same thing for a little bit cheaper in terms of number of parameters. So really long short-term memory still is the main solution and is a drop-in replacement for simple recurrent networks. All right, so what is it? What are they trying to do? It builds in an inductive bias that solves some of the very problems that we were talking about before. We have to think, what are the kinds of things we want to do, right? Let's see if I can get it here. Right, these potential problems, right? All of the inputs being important. No, some things need to be dropped or removed. They don't even need to be considered for further memory retention, because that would just be a waste of resources. Making sure that you get that at the right time step is important. You may also even need to remove information if it's no longer relevant anymore. So picking what's important, picking when to remove it so we can clean up and keep clean resources, and also picking what's actually useful and using what's useful when we need it. Those are three important things we might need to think about. So you can think about it this way, right? If I'm trying to work on a time series problem, I need to at least know what to store, right? What is important to retain. Also at the same time, when I'm storing things in memory, when I'm writing a program, I've got to know sometimes when I maybe need to clear memory out or get rid of things because they're not needed anymore, right? So I pull those things off the stack or throw them away because I'm done with them. I just don't need it anymore. That's also something we have to worry about because we have limited resources. And the third thing is that I've got to know when to use those resources wisely to accomplish the task at hand. Even if I store it, I have to know when I can use it. And I don't want to have it using it all the time. I only need to use it when it's relevant, right? Other times I don't need to touch it, or I don't need to let it interfere with my processing. Most of the time, neural networks in a feed-forward fashion kind of see all of the input or everything they're dealing with simultaneously, all in the same instant. So we have to solve these three different problems. And LSTM is built to try to solve those three different problems. So let's take a quick look at the architecture. We're going to get into this a little more in class because I think we'll review it some, and there's details here. This is actually a picture from the original paper that shows one unit. This is one neural unit in an LSTM layer. Okay, one neural unit. So there are a lot of components here. Now the good news about all the components in this figure is that every single one of them are components that you have seen before. They are not really new things, but when you put them together like this, they look like they're this really strange new thing that you've never seen before. But it's all built out of neural components that you have already seen. Okay? But we use this to create just one neural unit in LSTM. How do we do that? Okay, now at the beginning, first of all, every neural unit receives a weighted sum from inputs coming in. So whatever the layer is prior, right, you're getting a weighted sum from the input layer. You're coming in, this is one unit in the recurrent layer. It will receive a weighted sum. That's its net input. So keep that in mind. That's the net input coming in. Now in this this very first older versions, I don't think this happens as much now with LSTM. Older versions then used to do this thing called input squashing, which means they would then pass that through a sigmoid activation function first, this GNetC. That's a sigmoid activation function, and then propagate it through the rest of the net. In many practical implications these days, I'm not so sure if this is done or not, but we kind of do this to make sure that we're putting some of this information in, right? What's more important is that you have this thing over beside it, which is called the input gate. And this one is retained. So I'm pointing this out to you because I think in modern implementations, this input squashing gate is largely removed. Even if you put it in, it doesn't have a huge impact either way. That's also the reason why it was removed. It doesn't seem to impact performance much. It's a bit redundant. And I'll explain why. But what you have now is the idea first that I need to know whether the information that I'm receiving in is worth storing or not. Like I'm receiving this weighted sum. Is this information that should go into this unit? And should it have it for consideration? So there's this separate little unit over here, and this is operating just like a standard unit. It's actually receiving input from the exact same layer that this input was coming in. It's a separate set of weights. We call that the weights for the input gate. So it takes those inputs, creates a weighted sum, and passes it through a sigmoid. So that's just a standard neural unit. It's like you have multiple units inside of this bigger unit. But once you have the net input from the unit itself, you then take this weighted sum, calculate a sigmoid. Remember that value is going to output something between 0 and 1, right? So something between 0 and 1. It then takes that, and these little dots here are symbolizing multiplication operations. So whatever that scalar weighted sum was that came in, right, the net input goes down to one value. You then take that and you multiply it times the output of this sigmoid. If that sigmoid happened to produce a value near 0, it would basically be multiplying that weighted sum times 0. It would say that weighted sum is not important, or it wouldn't send that signal into the rest of the unit. But on the other hand, if that sigmoid produces a value near 1, then it would send all of that weighted sum to the center of the unit for processing. The idea is the input gate acts as a filter to decide what fraction of this weighted sum actually needs to be processed by this unit. And that is a way of protecting it from interference, right? If this unit is maybe holding on to some very important information, maybe we don't need to be distracted by this current input right now. And the input gate can learn to make a decision about how to filter that input out, whether it should or should not. So that's the input gate's function. Once that's done, whatever is left, that weighted sum multiplied times that gate, gets passed on to the central cell. Now the central cell itself is really just a simple storage. Like it just stores one value. That is basically kind of like the net input, you might say, of the unit. And then it has a recurrent net weight that it always feeds back times itself. But that weight by definition is typically 1. It's usually set to 1 so that you get a perfect feedback, right? It's always going to remember that thing. But sometimes you need to flush things out or forget what's in there because we need to clean up and remove things from memory. We don't need to remember it anymore. So there's this other component, which is another little neural unit, which also takes a weighted sum from the input, and it's called the forget gate. So it produces a value through the sigmoid between 0 and 1 based off that net input, multiply, take the weighted sum, pass it through the activation function. You now get a value between 0 and 1, and you multiply it times the value that's currently stored in the cell. So whatever its last activation value was on the last time step, it gets multiplied times the forget gate's value. If the forget gate is outputting a 0, it's like zeroing it out, or flushing and getting rid of the information. If it's set to 1, it's like it's retaining that information. And by retaining, I mean it will also be then a combination of this plus whatever was coming in through the input gate side. So if the input gate decided to let stuff through, it just gets summed up with whatever was already there. But if the forget gate told you to turn it off, then it would just replace it, right? So the forget gate and the input gate have to learn over time to work in tandem for both data protection and removing data. Also, there's another mechanism. As we come out through here, output squashing is still typically retained. This is usually a hyperbolic tangent. We usually use a hyperbolic tangent activation function for an LSTM architecture. So it has an output between -1 and +1. But we also have this output gate. This is also taking the input to the unit, taking a weighted sum, again a different set of weights, producing an activation value through a sigmoid. That's now a value between 0 and 1 that you multiply times that activation. The idea is the sigmoid will scale the activation. If the output gate is outputting is 0, then none of that output moves forward. It gets multiplied times 0, and it's like the unit is silent and doesn't really pass anything downstream. But if that output gate produces a value of 1, then you multiply that activation times 1, and it sends its full activation value downstream. The idea here is that the output gate acts as a sort of filter to make sure that it doesn't distract any downstream processing if that information that it's holding on to is not useful yet for the task we're trying to solve. And then when it does become useful or needs to be released, the output gate can then open and allow that information to flow. So this is just one neural unit in the LSTM architecture, but it's like it consists of these, it's like it is a unit, right? A net input with a hyperbolic tangent activation function, but it has this little recurrent connection on the inside, right? So it's like a recurrent unit, but it has these 3 gating mechanisms set up. These gating mechanisms are the inductive bias, right? We are pre-wiring the network to have these 3 functions of input filtering, forgetting or flushing out, and then output filtering. And these 3 things are what we often use for sort of read-write type operations on memory, right? We have to know whether we should overwrite a particular variable. We need to know whether we need to delete a variable. We need to know whether we need to take that variable and use it and pass it to our next function so that it can use that value. All these different things are considerations that normally a model would have to learn on its own, somehow through a complex learning process that's dealing with exploding and shrinking gradients. It's very unlikely you'll find a set of weights using this architecture that actually does these types of intelligent operations. So what we do is build in LSTM. Instead, it has an inductive bias that makes it form representations that are useful for memory tasks. It makes it form representations of input gate filtering, forgetting and clearing, output filtering to prevent distractions. All of this is something that is baked into the architecture so that the neural architecture can just learn to adjust these weights, and that allows it to take advantage of that inductive bias from the very start. So it's able then to leverage those weights for that purpose under this idea that these are the important things we need to do with memory. And it does turn out to be the most successful inductive bias for recurrent networks that we've found so far. Now, the only sort of downside you could think about is there are additional parameters, right? Lots of sets of weights. They're much more complex neural units than a simple recurrent network. That's true. And so those extra weights are there. The good news, though, is that all of this, despite the fact that it's very, has more weights and therefore has more parameters, every single operation here is a differentiable operation, right? All these multiplication operations, going through all these activation functions, these are all typical architectural components, things we've already been using in our deep learning so far. So gradients can be passed through all of these components. And importantly, this architecture, although it's not in the original papers, is also perfectly compatible with skip connections. You can imagine easily having a residual connection that skips around this recurrent unit cell, and what it's actually calculating is some kind of nonlinear recurrent residual that it's passing downstream. So with all that in play, we actually have the ability to stack LSTM to create very deep architectures as well, without any worry about these gates just not really behaving well or squashing the gradients in some strange way. Because we do have hyperbolic tangent and sigmoids involved. So there could be some concern about that, but with residual connections we can alleviate it. So with all that in mind, this is the best, most successful architecture to date for dealing with recurrent problems. So in class we're going to look at some codes and see how these particular models behave on various time series tasks. And then we'll get into some new architectural changes next week. But these are our primary architectures that we're going to be working with. Simple recurrent nets, which is this basic architecture which we train with backpropagation through time. We also train LSTM naturally with backpropagation through time, but it does turn out to be more robust and not as sensitive to these problems of exploding and shrinking gradients. Why is that? Why would they not be as sensitive to exploding and shrinking gradients? Well, importantly, I just told you a minute ago that little recurrent weight is usually set to 1 by default. And what that means is that that weight is set right at 1. by default, and it doesn't get updated. It's always just trying to use the forget gate and the input gate to fold that information together. It's never using that weight over and over again in the way that it would cause the activations to either shrink or explode, right? If the weights were greater than 1, you're at risk of exploding gradients. If they're less than 1, you're at risk of shrinking gradients. But if you put that little recurrent rate right at 1 and instead distribute all the rest of the responsibility of learning to the gates using that inductive bias, then that means you're not in any danger of having exploding and shrinking gradients. They mitigate much of that problem. So with this in mind, this is how we expect that we can use this more effectively, and it should learn more effectively than the simple recurrent architecture. It's just an inductive bias designed specifically for these kinds of tasks. So we'll get into the rest when we get to class. Until then, hope you guys have a pleasant weekend.